Okay, then we stop at lesson number 43. So we are going to continue with the past year questions right now. Okay, before we continue, we're having some quick revisions. Okay, so for normally most of the question for electricity, we were just using the concept that assume there is no internal resistance. Unless the question that mention, we only consider this case. Okay, most of the time we don't consider. Okay, then here, um, okay, when open circuit, we connect the voltmeter. Okay, so at here, when open circuit, that means that the switch is open, no current flowing, no current flowing. So the voltmeter actually is just straightly measuring the EMF, okay, EMF. So at here, voltmeter is equals to EMF 3.0. But once we close the switch, the current flowing through the circuit, we found out that the voltmeter no longer 3.0 volt. So right now, the voltmeter is not measuring EMF anymore, okay, not EMF. But this voltmeter basically is measuring the voltage across the external component. Okay, so it's actually the 2.80. If I redraw the circuit, actually you can find out that I can redraw and make it parallel below the bulb, below the lamp. Okay, so this 2.80 actually is measuring the potential difference across the external component. Okay, so why there is a losing 0.2 volt is because voltage drop is because when current flowing through inside the battery, they have some chemical reactions, so they will cause a voltage drop due to the internal resistance. Okay, when current flowing through the circuit is complete, actually inside the battery, so this one, this is a whole battery. The battery have acid internal resistance. Okay, it will take some voltage, so the voltage will drop, then the rest will go into the external component. Okay, so today we using the graph to find the informations. So two things that you have to know is when y-intercept, the value is actually the maximum value for the voltage is actually the EMF. Okay, it's EMF. So at here, this one, why I know this reading is EMF is because you see this is current. When current is equals to 0, what does it mean? Circuit is open. Okay, when circuit is open, so this maximum value is actually the EMF. Okay, so when current start to flow, we found out that the voltage will drop. Okay, the voltage will drop is because inside here we have the internal resistance. So how we know how big of the internal resistance? Actually, we can calculate by using gradient. Okay, we can calculate the gradient. So from the gradient here, I know that that is my internal resistance. Okay, so from the graph, we can know these two. Okay, we have to know these two. Y-intercept actually is the EMF. Then gradient is actually the internal resistance. Okay, so we come back here. Okay, this is 2021 past year questions. Okay, here first. A battery of EMFE and internal resistance is connected to a variable resistor of resistance R. Okay, so at here, an ammeter measure the current in the circuit. Okay, current flowing through the external resistance and current flowing through the internal resistance is the same current I here. So if I want to know the current flowing through the internal resistance, actually I just find out using this part also can. Okay, I can using, let's say this one just now is 3.0, here is 2.8 volt. Okay, so I can using the 2.8 volt divided by resistance, so I know the total current here. Then from here, the total current, I know that the current flowing through the internal resistance. Okay, they are the same. Okay, next, the resistance R is now varied to change the value of I and V. Okay, so this is a variable resistor. So this resistance value can be changed, okay, manually changed. So this is the variations of I of V is shown in the diagram. Okay, most of the time, when we say IV graph, we will get this because it follows Ohm's law. And this is a perfect case that we don't assume internal resistance. Okay, once you found out that the V and I is not a straight line passing through origin, here V and I or against V, doesn't matter. So that means that in this kind of case, voltage is dropped. We are considering this case is having the internal resistance. Okay. So at here, use the figure 5.2 to state the EMF of the battery. So from the graph, what is your EMF? Very easy. Tell me the answer. From the graph, how you know what is the EMF? Yes, Vashini already told us. EMF is 2.4. Okay, so this one label 2.4. So at here, when I is equals to 0, your voltage is 2.4 volt. This voltage actually is EMF. Why I know this is EMF? When no current flowing. So this is an open circuit. Okay, open circuit. Okay, so next, using the figure 5.2 to determine the power dissipated in the variable resistor. Okay, boys and girls, need to read the question carefully. They might asking you power dissipated in the internal resistor. So the answer will be totally different. Now it's asking you variable resistor when there is a current of 5.0. Okay, when in the circuit at here, current is 5.0 ampere. So at this part, what is the power dissipated at here? Power, we have three formula. Actually, no matter which formula you use, you will get the same answer. Okay, so power equals to V times I, power equals to I square R, power equals to V square over R. Okay, this one is VI graph, V against I. So that means that very straightforward, we can just using this formula to do calculations. Okay, so at here, question say 5 ampere. Okay, so from the graph, you can use the 5 ampere to find the voltage and then you do calculation. Okay, you do it right now. Yes, Vashini, correct. Fatima, you let me have a look. Fatima, you check what is the voltage it will have when current is 5.0 ampere. What is the voltage across the resistance R? How about others? Tell me the answer. Okay, let me check Wesley. Wesley, correct, but the problem is your unit is wrong. Manjo, yes, correct. Okay, so dear here, when you are 5.0 ampere, so this is your voltage, which is 1.3 volt. Okay, so power is equals to voltage is 1.3 times the current is 5. So your answer should be 6.5 watt. 6.5 watts. Yes, Wesley. Okay, so dear, if you using others this value to do calculation, you will also find able to find the same answer 6.5 watt. No matter what method you use, you will get the same answer. Okay? Okay, let me have a look. Okay, now I want to emphasize the things is here, you see this reading Y 1.3 is for this part. Y 1.3 is the voltage for this part. Voltage R is 1.3 volt. So here is 2.4 volt. Okay, because when you are connected across the cell, okay, voltmeter connected at here. This is voltmeter. Okay, like what I told you when we close the circuit. Actually, this one, the voltmeter reading no longer show you the EMF. It's showing you external component, voltage across external component. So actually, this reading 1.3 is exactly for the resistance R, okay? For the voltage across resistor R. Okay, now another things that I want to emphasize at here is you need to read the question carefully. Now they want you variable resistor. They can ask you power dissipated in the internal resistor. Okay, internal resistance. So if they're asking you about this part, the answer will be totally different. Okay, how we do calculation for this part if they're asking you internal resistance? Okay, so 2.4 you have to minus 1.3. From here, you know how much voltage will be given to the internal resistance. So you got the V. Then how about your I? Because this is a series circuit, see? Series circuit, as I told you. This is the current, let's say 5.0 ampere. Question asking you 5.0 ampere. So that means that the current flowing in the internal resistance also 5.0. Okay? So if they're asking you calculate power dissipated in the internal resistance, current is the same 5. But the voltage, you have to look at here how much voltage will be dropped across this internal resistance. So answer is 2.4 minus 1.3. The answer here, you substitute in. Okay, so you need to read the question carefully. Okay, so the answer for this one is 6.5 watt. 3 marks, boys and girls. Don't forget, always have the habit, write down formula, substitution, final answer with unit. Okay. Step 1 is represented by the value of the gradient. Value of gradient represent what? Just now, we already told you when y-intercept is actually EMF. Then how about gradient? Foul wrong. Cannot foul. What is represented? What we represented? If y-intercept we represent EMF, then gradient represent what? The value that we calculate from the gradient actually is representing what? What physical quantity? What physical quantity is represented by the value of gradient? Fawal, your answer not correct. Manjo, yes, Manjo correct. Fatima, same as Fawal. You cannot say resistant, cannot. Resistance, so many resistor at here. You want to talk about the external resistance or internal resistance? That is the problem. Okay, so at here, this one just now we got recall here. The gradient is represent negative R. Yes, so Vashini is correct, but we will write in words. So the value actually is negative internal resistance. Cannot write resistance only. Resistance, we got 2 resistor at here. Okay, we got 2 resistor, this one and this one. Which one you want to mention? So we are mentioning this internal resistance. Gradient is negative internal resistance. If you only write internal resistance, also correct. Negative or not negative, this one in the answer scheme they accept. Okay, gradient is negative internal resistance. Cannot accept answer with resistance only, because we got 2 components here. Okay, until here, any question? If no question, we goes to the question number 4. Fawa, okay, okay. Only Fawa, okay. How about the rest? Okay, wait. Okay, okay, let's go. Okay, a battery of EMF E and internal resistance R is connected to a variable resistor of resistance R, as shown in the diagram 6.1. The current in the circuit is I, and the potential difference across the variable resistor is V. Explain in terms of energy why V is less than E. Why? So we did this question before that, if not mistaken. Let me check. Last time I got told you this one is important. Where is it? Yeah, here. Okay, here okay, here. Yes. Okay, why the potential different across the battery terminal? That means that the voltage across the component. Why is always less than the EMF? So EMF at here is 6 volt. So for this part, the voltage across the external component, this part confirm is less than 6 volt. It might be 5.8 volt. Okay, why less? It's because some of the energy is dissipated in the internal resistance. Okay, some energy is lost or dissipated at here. Okay, due to the internal resistance. So this is the answer. Can you see that two past year questions asking the same idea, asking you to explain? So okay, here we write together. Why in terms of energy? Okay, this is only 1 mark. Just now the question is 2 mark. Okay, that's why we are giving the definition for the EMF E. Okay, in terms of energy driving one column of cell. Okay, around the complete circuit. Okay, so at here this one only 1 mark. Then we're talking about the internal resistance. So energy is dissipated in the internal resistance. So this kind of question they like to ask you. Okay. State an equation relating E, I, R, V. So you should already familiar with the formula, especially if you are graduate from SPM. Okay. This is not a new topic for you. Okay. So at here, EMF is E. Okay. EMF is E equals to the V plus IR. Okay, if question is E, then R, then R, then I. Okay, what is our answer? Your answer should be E equals to I R plus IR. Or E equals to I R plus R. It depends on what physical quantity they're giving it here. Okay, so I just tell you that if let's say they didn't write in terms of V, they give you I and then the external resistance R and then internal resistance small r, and this E is actually EMF. So these two will be our answer. So these three formula actually is the same formula lah. Okay, it just depends on what information we have. Okay, should be no problems. So I go down. If I'm too fast, please let me know. Okay, the resistance R of the variable resistor is vary. The variations with I of V is shown in the diagram 6.2. Okay. Explain how it may be deduced that EMF of the battery is 2.8 volt. How you know? How you know the battery EMF is 2.8? Okay, so better you don't tell me because y-intercept is 2.8. Not really answering me the question. How you know y-intercept is actually your EMF? How you know? So any of you can try. How I know 2.8 is my EMF? Okay, if you say because y-intercept of the graph is 2.8, not really answering the question. Okay, then y-intercept, how you know y-intercept is EMF? Any of you can tell me? When just now quick revision, actually I got mentioned y-intercept, that reading is actually our EMF. Any of you? Vashini? Manjo? Yes, Vashini, correct. Because when y-intercept 2.8 is EMF is because current is 0. Okay, when current, Manjo, correct. Wesley, when current is 0, there is no internal resistance. Yes. So the V is actually maximum V. That is our EMF. Yes. So the keyword is when current is 0. Okay, the V is 2.8 volt. That is our EMF. Okay, no internal resistance. When current is 0, no internal resistance, so your maximum voltage is actually 2.8. That is our EMF. Okay, here answer scheme they also accept if you mentioning graph show maximum value of potential difference is 2.8 volt. From the graph, it's showing you maximum potential difference is 2.8 volt. They accept this answer. But I like this answer also. Easier, okay? When I is 0, here is 2.8 volt. So I is 0, that means that circuit is open. Circuit is open, that means that you are measuring the battery directly. That is your EMF. So this one is your EMF. Okay. Okay, next question. Calculate internal resistance. Can you guys calculate for me? Internal resistance. Do it right now. Jore, yes, correct. Too much show working stat in your paper, huh? Here no need. Since you get the answer, so I believe that you do everything correctly. Yes, Vashini, correct. Manjo, yes. Okay, should be no problems, right, dear? Okay, so at here, I can using this one, gradient. Gradient, so we draw a triangle. Okay, gradient, we draw a triangle. So here, this point is 1.5. So here is actually 0.7. So here is 0, then 2.8. Okay, gradient is 0.7 minus 2.8 divided by 1.5. So here I get negative 1.4 ohm. But you don't write negative 1.4 as your internal resistance. Cannot, because gradient is negative R. So your negative R, that means that your R is 1.4. No negative, okay? No negative. Do not write negative 1.4 for your answer, final answer. So R is 1.4 ohm. Okay, so this answer. Okay, next. D, question D. The battery store 9.2 kilojoule of energy. The variable resistor is adjusted so that your V is 2.1. Okay, your V. So I go down here. So here is 2.1, 2.1 volt. Use your figure 6.2. So use this graph? Use this graph to find resistance R. What is your resistance R? Okay, so again, here, this resistor is 2.1. This voltage across this resistance is 2.1 volt. So from the graph, this part is the voltage across the component. So you have to find 2.1, go here, and then find what is your current. Okay, so do calculation, what is your resistance? Okay, do it right now. Vashini, correct. Fatima, correct. Yes. So there they tell you the variable resistor is 2.1. So from here, we go 2.1, go here, and then I know that the current flowing through the resistance. Okay, so here, this one is 2.1 volt. Current is 0.5. Okay, current is 0.5 ampere. So can you see that here? V, I, so I can count R. Okay, donkey here, donkey. Question D1. So V equals to IR. Voltage across resistance, variable resistor, and then this. Current is 0.5. Resistance for the R, I don't know. Voltage is 2.1. So resistance is actually 4.2. 4.2 ohm. Okay? So you must be very clear. This graph, actually this V, when current flowing, this V is the voltage across external component. Okay? So next question is asking you, can you calculate number of conduction electron? Okay, number of conduction electron. So this one, last time I told you, I want to differentiate it out, so I can using capital letter N. Okay, in a time, so this is T. So number of electron flowing through the battery. So how do I know what formula I can use? If you already know, then you can start. If you don't know, I give you some hints here. Okay, any of you get the answer? If you don't have the idea, then here is the hints that I can give you. We are using this formula. And then E is the constant value that we have to know. What is the charge for one electron? Wesley, correct. Yes, good job. Okay, E is 1.6 times 10 power of negative 19. If you really forget, actually in the second page, data information they provided. Okay, Manjo, did you do something wrongly, or maybe you typing wrongly? Times 10 power of how many? Vashini, yes, correct. Okay, the current. How I know the current? You know. Just now from the graph, we know that from graph. Just now from the graph, we understand that when the voltage is 2.1, then the current is 0.5. 2.1, then 0.5. So this one is 0.5. Okay, 0.5. Yes, Manjo, correct. Typing error, right? 3.1 times 10 power of 18. Yes, power correct. So N is equals to 3.1 times 10 power of 18. No unit for number. No unit for number. Okay, by the way, when we do more question, and then actually this idea will be just this value that we already very familiar lah. Okay, so any others question? Should be fine, right? If you don't know where is the I, so you must be very clear about the question. What the question asking? When V equals to 2.1 volt, the whole circuit current is 0.5. How I know? From the graph here. From the graph, we already know. Okay? You see, this one is D. So this question is split out 1, 2. So that means that this second question, you still can using this information. Okay? Information in the paragraph D. So next, determine the time taken for the energy in the battery to become equal to 1.6 kilojoule. Okay, I give you some hints. Starting the battery is 9.2 kilojoule. Starting 9.2 kilojoule of energy. This is starting total energy in the battery. But at the end, it become 1.6 kilojoule. That means some energy loss. Okay, some energy loss in the battery. Okay, the question asking you how long the time. It dropped until 1.6 kilojoule. Assume that the EMF of the battery and the current remain constant. Okay, so since energy, formula for energy, E equals to VIT. Year 11, we learn E equals to VIT. So this one is the battery. So battery, highlight battery. So the voltage for battery actually is EMF. This E is not EMF, this E is energy. Okay, they're having the same symbol. So sometimes you will confuse, but cannot confuse. E equals to VIT. The E at here is talking about energy. So energy change, how much energy change? And then what is the V, voltage in the battery, which is the EMF? Then how much current flowing through the battery in the battery? Okay, and the time, how long the time? How long the time? The time is the one question want us to count. So do your calculation. How long the time your energy change from 9.2 to become 1.6? So how much energy lose, and then how long the time you need? Jore, no. Jore, you tell me what is the energy you use in the formula? Washini, correct. Yes, good job. And Jore, you tell me. Let me have a look. Manjo also no. You same as Jore. You tell me what is the value for your E you use. You use 1.2 or what is the value you use? So this one, energy loss. How long the time you need for the energy to drop from 9.2 to become 1.6? So how much energy lose? Okay, Wesley. Wesley, no. Wesley, don't forget about the prefix. Manjo, no. Manjo, no. Okay, so dear, here, from here change to here. So energy loss is 9200 kilo minus 1600. So we drop this amount of energy. Then how long the time we need for it to drop such kinds of energy? So at here, your V is your EMF. So your EMF in this diagram is 2.8, right? 2.8. So this one should be 2.8. The current in the circuit. So boys and girls, just now, when voltage is 2.1, okay, the current in the circuit is 0.5. So what is the current flow out from the battery? Also 0.5. Although just now we get 0.5 is because from here, I know that it's 0.5. But for the battery, because this is a series circuit, so it's still 0.5 in the battery. Okay, in the battery. So here, this one should be 0.5. So how long the time T? Okay, so this is your answer. Here, I want to emphasize, question talking about battery. So at here, the energy equals to VIT. The V at here actually is the EMF. Voltage in the battery is called EMF. Manjo, you count it and then you get the wrong answer, right? So cannot. Fawal, yes, Fawal correct. Okay, 5400. Or you say 5.4 times 10 power of 3 seconds. Okay, so this question not only one question like this, later on got another one question is also asking in the similar way. So that means that this kind of way they ask actually is quite common. So we have to know we minus the energy loss. So I know that it lost this amount of energy, then how long the time it needed. Okay, so we goes to your next page, page 19. Okay, is it okay already? Fatima okay, Fawa okay, Washini okay, okay, good job. Okay, Manjo okay. So dear here, define the EMF of a source. So EMF, 2 marks, you see at here, 2 marks. 2 marks. Second part of the definition is very important. Okay, so right now I write down the definitions from the answer schema. Energy transfer by source driving charge around the complete circuit. Okay, dear, second part, around the complete circuit. This is 1 mark here. Then here, energy transfer by source driving charge is another 1 mark here. But for me, I would like to write energy transfer by source in driving 1 column of charge. For me, it's more complete, but 1 column of charge around the complete circuit. Okay, if today this is potential difference, then answer will be energy needed or energy transfer in driving 1 column of charge, okay, across the component. Or we say from 1 point to another point. So for the second part at here is different. Okay, so EMF formula is work done divided by charge. So if potential different, also work done divided by charge. That's why their definition is very similar. Only the second part is different. Okay. So sometimes you will see that is what work done in driving 1 column of charge around the complete circuit. Also can. Work done is energy. Energy is work done. Energy transfer is actually work done. Okay. So finish writing down the definition. Can we proceed? Okay, so we go down. Circuit shown in the figure 5.1 contains a battery and EMF that has an internal resistance and a variable resistor, voltmeter and ammeter. Okay, good job. The reading from 2 meters are taken for different setting of variable resistor. Okay, so they adjust these variable resistors by changing the current. Okay, by adjusting this resistance, change the total current. Then from the total current here, they observe what is the voltmeter reading. Okay, so here this is the figure 5.2. Next, explain why V is not constant. Okay, why not constant? Why not like this? Okay, IV, then V is constant. Why not? Why not like this? Okay, so at here is easy. Because what? Inside got what? Inside got internal resistance. Okay, the V starting here the V. Okay, this part starting here the V is EMF, but the V will continue drop. It's because some voltage is given to the internal resistance, because inside we got internal resistance. Okay, so we write down first point, 3 mark here. First point, we can write that there is a potential difference across the internal resistance. Out. Okay, V. Now we're talking about V. So now I'm also talking about potential difference V across the internal resistance. There is a internal resistance also share the potential difference. Okay, so this is first point. Second point we can write is, you see from the graph at here, the current, we change the current. When current change, the voltage in the internal across the internal resistance also change. Okay, when current change, current increase. Okay, because here E equals to V plus IR. Okay, so this part is actually voltage across the internal resistance. Voltage across the internal, or I write small r. Okay. So when there is a change in current, of course your overall V internal resistance voltage is actually also changes. Okay, so here we write change in current. Okay, result in a change in potential difference because the internal resistance. Okay, when current change, your voltage across internal resistance will also change. Okay, this is second point. Then third point, why V is not constant. Okay, so when your voltage across the internal resistance changes are increased, because I increase what? I increase, then your IR also increase. So your V here will drop what? It will change what? Okay, it will change because your EMF at here, this is a constant, unchanged, constant. So if voltage across the internal resistance, you get more share, then voltage across the external circuit will get less share. Okay, so at here, there is the point. There is a change in potential difference across the internal resistance. I write small r. Okay, will cause a change in your V. So can you see that we're talking about V? So here, potential difference across R. Okay, then there is a change of potential difference across R, then change in V. Okay, you write it down. So if I rearrange the formula, V equals to E minus IR. Why V is not constant? Not constant, it will change. Why it will change? Why? Why is not constant? Because this one is constant, it won't change. So our explanation have to talk about this part. Get it? Okay, question asking you why V is not constant. Why V is not constant? Because the E is the EMF, this is a constant value. So our explanation only can talk about this part. So first, we're talking about there is a potential difference across this internal resistance. So when current change, of course, this part voltage will change. So if this part change, then your V will also change because of this formula. Okay, so sometimes in order to let the examiner to understand well, you can also write the formula down. Okay, write the formula inside your explanation. Okay, 10 seconds for you to write down these three sentence for 3 marks. Okay. So for the battery in B, use the figure 5.2, determine your EMF. Okay, dear, determine your EMF and then tell me your answer. Wesley, how you get this answer? No, Wesley, no. Careless. I think you're careless. You check again. Farwell, no. You read the scale. I think you read the scale wrongly. Washini, correct. Manjo le, Manjo. Fatima, no. How you get this answer? From the figure 5.2, determine the EMF. EMF is when current is zero. What is your voltage? That is your EMF. Manjo, no. Manjo, read again the scale. Okay, so dear, you must be very sure. You cannot straightly read from here and then go here. No. Okay. When EMF is when current is zero. So when current is zero, here. What is your voltage? So you have to extend your line. Wesley, correct? Wesley, but by the way, just now, is it you read wrongly? Okay, let me check. Yeah, okay. Careless. Cannot careless, because after that you're using this value for the working step, the continue question. Well, something like this. Okay. Put your ruler here, connect the line. Okay, I can connect until the end. Okay, somewhere here. Okay. Okay, so at here, this one half between 6 and x, so here is 7. Then here this point should be 7.4. This is the correct answer, 7.4. Yeah, Hawa also read it wrongly. Okay. So here 7.4 volt. So be careful. You see, normally this one, after that we will use this. So if here you read wrongly because of careless, I believe you guys can answer this question. But because we careless, our careless, then at the end this mark also will be deducted by 1 mark. Okay, we can accept your what we say carry forward mark, but final answer still wrong. Wesley, oh, I use the gradient. Gradient is find internal resistance, dear. Why the internal to find internal resistance? Then use the formula. But gradient is internal resistance. Okay, here. Okay, maximum current that the battery can supply. What is the maximum current can be supplied by the battery from the graph? Fawal, yes. Fawal, yes. Maximum current. Here is current. What is your maximum current you can have in the circuit? Vashini, correct. So dear here. Oh, I didn't draw it properly. So let me draw again. Somewhere here. Okay, here. So this one should be 0.92 ampere. Okay, this is the maximum current, I max. So answer at here 0.92 ampere. 0.92 ampere. Fatima, maybe I draw wrongly and make you confused. You redraw again the line. It should be 0.92, correct? Okay, what is the internal resistance? Okay, can we using the formula that E equals to V plus IR to find your R? Okay, at here, if you have all the others information, doesn't matter, you can find by using formula. But the problem is, I don't know about this. I don't know. Wait. Let me what is the current? Then what is your I? What is your E? E you have 7.4, but V you have to do a lot of working set to find, and so on. So at here, from this kind of graph, as I told you, two information of physical quantity we can find. One is y-intercept. Easy. Y-intercept is EMF. That's all. E. Second, gradient. Gradient is actually finding your R, internal resistance. So can you find internal resistance from the graph for me? Do it right now. Wow. No leh, Wow. Just now, did you able to get 0.92 and 7.4? If yes, you're using these 2 points. Yes, are you using these 2 points? Jore, no leh, Jore. Fatima, yes. Sorry, Fawal, yes, Fawal, yes. Fawal, my bad. Sorry, it's my bad. You're correct. Answer correct. But Fawal, I want you two significant figure. Vashini, very good. Two significant figure, correct. Okay, so dear, we can using these 2 points to do calculation for the gradient. So at here is gradient is actually this is 0.920. So 0 minus 7.4 divided by 0.92 minus 0. So my answer at here I get negative 8.0 ohm. Not ohm. This is gradient. Okay. So equals to negative R. So what is my internal resistance without negative anymore? So my internal resistance should be 8.0 ohm. Okay, here I want to emphasize 8.0 is two significant figure. Okay, if you study the answer scheme, they never having one significant figure. There were always two significant figure. This is 2 to 3. Okay, this is a suitable number of significant figure. Manjo 6.6. Manjo, check which part is wrong. Okay, those who already done for this part and you're able to get 8.0, can you read the question D and think? So Manjo, which part you made mistake? Is it you using the wrong point or what? The rest of you, you try with question number D and think. How was your second line, teacher? I take the middle one. Okay, you wait me for a short while. I check the answer scheme whether they got mentioned except plus minus or not. Wait me for a short while. This one is 2021 May June. If I'm not mistaken, actually they only accept this answer. 2 3 paper 2 3 question 5. Let me check. No, dear. Only this answer. Because is it Jory? Oh, Jory. Okay, because Jory, just now the question 1 and 2, they must be 7.4 volt for EMF. They must have the maximum current 0.92. So they only accept with this answer, and then your gradient using these two. So they didn't accept with others answer. They didn't mention they accept plus minus or in the range. No. They straightly write 8.0 as their final answer only. Okay, Manjo, okay. Okay, boys and girls, you already read the last question here. On figure 5.2, sketch a line to show possible variations with IV for a battery with lower EMF. Okay, so E lower, EMF lower. Then internal resistance R is lower than the battery in your B. Your line should extend over at least the same range of current as the original line. Okay, same range of current as the original line. Okay, so at here, from the graph, EMF, how I know? Y-intercept. Internal resistance, how I know? Gradient. So EMF smaller, that means that your Y-intercept also lower value. Okay, lower than just now. Here is 7.4. That means that your new line should be less than 7.4 because right now you're having a lower EMF. Okay, so next here, internal resistance is represented by the gradient. So internal resistance lower, so your gradient should be lower. Your gradient should be lower. Okay, so this one, this one is the gradient. So you having a lower than this. That means that less steep. Okay, less steep. Higher gradient, that means steeper. Okay, so lower gradient, that means that less steep. So they say that they want same extend over at least same range of current. So that means that they expect your current also until 0.92. So how your line? Okay, so your line right now lower gradient. So that means that it will be less steep. So something like this, less steep. And then is same range of current. So my final point, I still making it at 0.92. Okay, lower internal, no, lower electromotive force, EMF. So we can start from any point at here, any point. So you, as long as you're having your gradient is smaller gradient, then your EMF is lower EMF. That's all. That is your final answer. So I using another color line. Okay. So here 2 marks. 1 mark is straight line with negative gradient. That is smaller gradient. 1 mark. Second mark is your y-intercept on the y-axis, the v here, you have a lower value. So can be at 4, 5, 2, 3, doesn't matter. Okay, as long as gradient is smaller gradient, and then your EMF is actually lower EMF. And then just now they got mentioned your line should extend over at least the same range of the current as the original line. So I just make my line until 0.92. Okay. Okay, where my map, my mind map, where? Let me have a look here. Okay, so at here, this is the part that we already learned, DC circuit. Okay, we learned some symbol. All the symbol you have to know. What is the symbol for buzzer? So last time I already told you buzzer. Here, you see horizontal. So buzzer will be like this. Okay, if bell, shape of bell is something like this, right? Shape of bell, right? How I draw like this. Okay, shape of bell. Okay, so in the graph, in the symbol, it should be like this. Okay, so then EMF potential difference. You need to know in terms of energy how it transfer. Okay, for EMF is from chemical to electrical. For potential difference is from electrical to others form. If resistor, then it will have thermal energy. Okay, it will become hot when current keep on flowing. That's why we always say when you do practical, when you are not taking any reading, maybe you are plotting the graph. Okay, do other things. Okay, so please open the circuit. Do not keep on letting the current flowing through the circuit. So at the end, you will slightly change the resistance. Although we touching it, we cannot feel the temperature difference, but actually there is some thermal energy inside. Okay, so here internal resistance. This is the part that we keep on mentioning. So here when they say terminal across the cell, actually when the circuit is closed, okay, the circuit is closed when current flowing through, the voltmeter reading actually is for this part. Okay, is for this part, external resistance. Then this one is the internal resistance. Voltage drop is because internal resistance. So here, if you revise back the past year that we have done, okay, so at here they normally asking you lah, okay, when the resistor for the variable resistor increase or decrease, what happened to your voltmeter reading? Okay, so this is the relationship. So when resistance decrease, total overall resistance decrease in the decrease, so your current in the overall circuit is actually increase. Step by step explain. Okay, so they might be asking you something like this. If here I connect with another resistor, so you have to think. So what is your total resistance right now? Is increase or decrease? Okay, I add another resistor in series. So think again. What is your total resistance and what affecting your total current? Okay, so here total current, what's going on? Then from here you can know that what is the voltmeter reading going. Okay, so basically we're done for this part. So now we are going to the next lesson, next worksheet, lesson 44. Kirchhoff law. Okay, Kirchhoff law. We got two. So if no problems, we comes to here. Lesson 44. Okay, is it okay? Okay, Fatima, okay, everyone. Okay, good job. Okay, we got two law. One is called first law is related with the conservation of charge. Okay, charge is related with the current because current is charge per time. Okay, so here conservations of charge. So Kirchhoff's first law said that sum of current entering a junction, current entering the junction will be equals to sum of the current leaving, so it's out the same junction. Okay, so at here, actually when we learn about year 11 or from 5 we learn about electricity, we are applying the Kirchhoff's law. Okay, so here this is a conservation, a consequence of conservation of charge. Okay, boys and girls, highlight this. First law is talking about conservation of charge. Okay, then next, currents should not be increased or decreased in the circuit when it's split. Okay, so here if the circuit split into two branch, the current before circuit split should be equals to the current after it split. So Kirchhoff's first law said that I total, okay, this one is I total equals to I1 plus I2 plus I3. The arrow is so important. Here, this one is go in. Okay, so this one is in, current in. So this one is out from the junction. So this one is out. In equals to out. So this one, look at here. This one is go out. Here go in, go in. Okay, maybe I using highlighter. So this one is in. This one is in. Any others in? 5 also in. 4 also in. So at here, Kirchhoff's first law say I1 plus I2 plus I4 plus I5. Because this four actually is go into the junction equals to out from the junction, which is I3 plus I6. Okay, so at here, every single junction here or branch here, we need to label the direction of current. Okay, so from positive, battery here is positive, so current flow out from here. So current flow into, so this one is into the junction. And then it split out, so go out. So your 3 ampere should be equals to 2 ampere plus 1 ampere. So this one is current in equals to current out. Okay, should not be a big problem lah. Okay, we just apply our knowledge that we already know about the current in the parallel circuit. So this is a Kirchhoff's first law. So we goes to page number 2. How about Kirchhoff's second law? Conservations of energy. Okay, potential difference is energy divided by charge, right? Okay, energy divided by charge. We said that the energy transfer in driving one column of charge. Okay, right? So at here, Kirchhoff's second law is conservation of energy. So we are talking about the sum of EMF, or we say the potential difference now, okay, is equals to EMF, maybe like this. EMF equals to sum of potential difference V. Okay, around a closed circuit. So at here, this is a consequence of the conservation of energy. Highlight this one. Second law is talking about energy should be conserved. Okay, energy never be used up or lose in the circuit. Energy is transferred into the circuit is equals to energy transfer out from the circuit. Okay, so at here, how many energy is into the circuit? Into provided to the circuit, which is our EMF. So we got two energy provider, which is E1 plus E2. Okay, why is plus is also important. Here is positive, so current is going up. Here positive is going up. They're having same direction. So the energy that provided by these two cell or battery actually should be plus it together unless they are in opposite way. They're connected in opposite way. Then we need to using the bigger EMF minus the smaller EMF. So but right now the provided energy provided they're having same direction. So we just add it up. E1 plus E2. Okay, then equals to energy transfer out. What energy transfer out? For example, resistance, it will producing thermal energy and loss to the surrounding. Okay, transfer out. Voltage will drop due to the component. Voltage will drop due to the component. So what voltage drop? Which is the V1 plus V2. They use up the voltage. Okay, they use up the voltage. So at here, in is the battery EMF, out is the component. Okay, so at here, sometimes the MCQs, they don't really give you ABCD with this direct answer. They might be giving you like this: E1 plus E2 minus V1 minus V2 equals to 0. Actually, it's the same thing. Okay, so this one is provided. So here, Y minus is actually voltage drop due to the across the component, due to the component. Okay. So energy into the circuit equals to energy out of the circuit. Okay, so at here, if the circuit is in parallel, okay, in parallel, so that means that we got two loop, more than one loop lah. So like this is one loop. Here, second loop. They are independent. So in my worksheet at here, I using two color to show you loop 1 and loop 2. Okay, so at here, since they are same direction for the battery, so E1 plus E2. Okay, it will equals to the out from the circuit, which is V1 plus V2. Then full stop. Okay, so at here, I might be separated out. E1 plus E2 equals to V1 plus V2. So this one is the first one, I know. Second one, we can using second loop, which is E1 plus E2 equals to V3 plus V4. So this is second. Okay. Then you might be also saying that this is these two, E1 plus E2 is equal what? So V1 plus V2 equals to V3 plus V4, also correct. Okay. Then we can try some past year question. Theory seems like easy, then we try with past year question. Okay, can we go to page number 3? Okay, Vashini, okay. How about others? Fawal, Jory, Wesley, okay. Fawal, okay. Manjo, okay. Okay, Jory, okay. Okay, first one, very easy. Page number 3, very easy. Catcher first law, we got two. One is about, first law is talking about the charge, conservation of charge. Second law is talking about the energy. Answer is B. Okay, answer is B. That's all. Okay, now we look at here, single loop. Okay, we connect, we having two battery, we connect them together. Okay, what is the current I when I connect two battery together? How we solve this? Okay, first, you look at this whole circuit. Okay, as I told you, we label the direction of current first. This one is longer line, so it's positive from the battery terminal, positive. So current go out. Then 8 volt current here positive, so current goes to opposite direction. So can you see that this one current is here, then this one current in opposite direction. So if I draw it out, it might be like this. 12.0 volt. This is 8.0 volt. Okay, you imagine this one, you move until here. Okay, you make the wire, okay, in a straight line, make this part connect to here. Okay, so the longer line will be facing the longer line. Longer terminal of 8 volt will be facing the longer terminal of 12 volt. So at here, we will using total EMF, we are using the big value minus small value. So it should be 12.0 minus 8.0. So this is total energy provided in the circuit. Okay, because some of them is cancelled out by the 8.0 equals to the loss. Okay, loss, the potential difference out from the energy out from the circuit. So out is because of this resistance, internal resistance here. So here, voltage across the internal resistance will be the current times your internal resistance is 1 ohm plus 0.5 ohm. So your current, if you do all calculation correctly, your answer should be 2.7 ampere. Okay. Is that clear how we solve this question? Total EMF. Then you have to check whether it's same direction, same polarity of the battery or not. If same, then we just add it up. If different, okay, it's opposite directions. So we have to using a bigger EMF minus smaller EMF. This is the forward that provided in the circuit. Only provided forward. Then we got two internal resistance, which is 1.5 ohm. So the forward provided to these two 1.5 ohm. So current is 2.7 ampere. Okay, for this question, is it okay? Able to get the idea? Yes or no, dear? Okay, okay, good job. Then here, you try with this question. Can you try? What is your total energy input equals to the total energy out, transfer out? So it's the voltage provided by the EMF equals to the potential difference across the component. Okay, solve this question and then tell me what is the current I. Any of you can get the answer? Tell me your answer. Okay, Manjo, let me check. Manjo, yes, correct. Wesley, yes. First, label the directions of current from the battery. Then determine whether they are in the same direction or opposite. Vashini, correct. So this one, go out. This one, go out. So this one, positive, go here. Okay, so you will find out that this one and this one, same direction. But the forward is in opposite direction. So your total EMF here is actually 3 plus 2 minus 4. Because 3 plus 2 is 5, it's bigger. So we're using 3 plus 2 minus 4 equals to your voltage across the 5 ohm. So it's 5. Okay, so it's 1 equals to 5I. So I is 0.20 ampere. Answer is A. Okay, if in your paper 2, do not write 0.2 ampere. It's 0.20 ampere. Two significant figure. Okay? So boys and girls, we go to question number 4. Is it okay? Okay, Flower, okay. So here, okay. Three battery and three identical resistors are connected in the circuit PQR. The battery have negligible internal resistance. What is the potential difference between point P and Q? Okay, so that means that here, okay, I can draw somewhere here. So if let's say I have a voltmeter measuring these 2 points, what is the potential difference? Okay, here, I need you to calculate what is the potential difference across this resistor. Okay, how much voltage across this component are? How you do calculation? Do you able to find it out for the whole circuit first? What is your total EMF? Since these three resistors are the same, identical, then the total EMF will be shared by these three lah. So you will know how much will be used up by this component, how much voltage will be used up. So can you try step by step, calculate what is the voltage across this arm? From the triangle whole circuit, can you find out what is the voltage across one resistor? Any of you? Step by step, tell me what is the voltage across this resistor. First step, what I want you to find is what is the voltage across resistor. If you still cannot, then my question is what is the total voltage across the whole circuit? Okay, I got answer from Washini. Yes, Washini get the answer for the voltage across the resistor. Then Washini, from here P to Q point, what is the voltage? You guess. Wow. Okay, like dear, what is your total EMF in the circuit? So here positive go out. This one is in opposite direction. You see, this one is in opposite direction. So later on we have to minus because this one is in opposite direction. Then this one is going up in the same direction as just now. Okay, so what is your total EMF in the circuit? What is your total EMF in the circuit? Okay, it will be 9.6 plus 6.3 minus 8.4. So your whole circuit, your EMF should be 7.5 volt. So far, while you get until here only. But this is total EMF for three resistor. Okay, so at here we got three resistor, right? So the 7.5 I should divide it by 3. So I will get 2.5 volt. This is the voltage across one. So here we'll receive 2.5 volt. Here we'll receive 2.5 volt. Here we'll receive 2.5 volt. Okay, until here, do you guys able to get my idea? Until here. Okay, Amanjo, okay. So Vashini, correct answer. Okay, dear. So next step is, what is the voltage across this P to Q? Okay, so dear, here, you see, this one is 9.6 is provided. This one is resistor, it will dissipated to the surrounding. Energy will be dissipated to the surrounding. So this part is used up. So this one is drop. This one is provide. So in between here, I provide 9.6. Then you use up 2.5. What is the remaining? So V across PQ, it will be 9.6 minus 2.5. So your answer should be 7.1 volt. Answer should be C. Okay, so this part is gain or provide to the circuit. Okay, provided to the circuit. Supply to the circuit. Okay, this one is drop. Okay, because you use up drop 2.5 volt. We supply 9.6 from point P to Q. I supply 9.6, but the resistor will use 2.5. So at the end, I still have 7.1 volt. Is that clear? So answer is C. Yes. Fawal answer is C. Okay, okay. If I redraw the circuit, okay, I draw in another way round. So this one is my resistor. Then here is like this, like this, like this. Then here is like this, like this, like this. Then this is my another one. Okay, like this here. So this is a P point, and this is the Q point. So we measure the voltage across these 2 points. Okay, do you able to agree with what I draw? I just make this one is in series. What can you see? This one is in series. So I just draw it in one line. Okay, so at here, just now I told you 9.6 volt at here. Each of the resistor is 2.5 watt. 2.5 watt here, 2.5 watt. So this one is 8.4 watt. Here is 6.3 watt. Okay, teacher, you compare P point to Q point using this chart. Can we compare P point voltage PQ by using this part? Yes, actually you will get the same answer. Okay, so how we solve by using another path? Okay, here this one is positive, go out, and then we found out that this one is in opposite direction because this one is positive at here. So what should we do? What should we do using bigger EMF minus smaller EMF? So you will be 8.4 minus 6.3 volt. So 8.4, let me minus 8.4 minus 6.3 is 2.1 volt. Okay, 2.1 volt. Then in this part, I provided 2.1 volt. Then I drop 0. I dropped 5 watt. I dropped 5 watt. I dropped 5 watt. Okay, I dropped 5 watt. So at here, wait. If 5 plus 2.1, 7.1 volt. But why we need to add it up? Let me think. Oh, okay. Because just now the whole circuit we set as positive. So the 8.4 is actually the negative. 8.4 is opposite to the 9.6 and 6.3. 6.3. So at here I should get a negative. Then I drop here for this part actually is negative 2.1 volt. And then this part is 5 volt. So at the end 7.1. If like this explanation will be make you confused. So okay, dear, we just stick at here. Okay, what I calculate at here actually can, but we have to consider the whole circuit, how it run. Because in the current in the whole circuit, is 9.6 plus the 6.3 is higher. So actually we should follow this direction. The 8.4 actually should be in the negative. So at the end, here, this one, we will lose 2.1 volt because minus 8.4 volt and plus 6.3 volt. So it's minus 2.1. Then this one we drop again 5 volt. So it's dropping 7.1 volt. But if using this part, you might be confused. Okay, because we still need to consider the overall current. So we using this part is more easier lah. Using this part, the upper part. Okay, until here, is that clear, dear? Okay, Baba okay, the rest of you okay? Only Fawang? Washini okay? Manjo, is it okay? Jore? Manjo okay, Okay, dear here, if you okay, then we look at this. Okay, so this one is what is the potential difference between point X and Y? So at here, point X at voltage here. Okay, so first positive go out. Here positive go out. So here positive go out. Okay, so you look at this. This is the overall current in this direction. That means that this one is in the correct direction. This one also, this one also. So your total EMF should be adding up these three equals to the I times the total resistance. Okay. Then can you find what is the potential difference between point X and Y? Try before you refer my answer. Wesley got answer already? No. Wesley, no. Washini, yes. Okay, so dear, here. In the whole circuit, we got total EMF is 3E because they all connected in correct direction. So it's 3E. Power correct. So I times the total resistance, which is 3R. Okay, 3E equals to 3IR. We found out that E is equals to IR. Okay, between X and Y, I take this point, I take this path. Later on, I will take another path for you to show you, okay, to show you. So you look at here. E minus IR is because this one is supply. Okay, this one is we lose, we drop. Okay, voltage drop. Voltage drop. So this part is drop. So we minus. So E minus I times R. I times R, just now we already know I times R is E. So E minus E is actually 0. Okay? So voltage across XY is actually 0. Then if we consider the upper part, can or not can? Like this. Okay, so this one is E. Here is E. Here is R, R. Okay, between here is X and between here is Y. So here is voltage across XY is equals to 2E. Okay, 2E minus 2IR. Voltage drop due to the the small r component. So at here 2E minus 2IR is E. So it's actually 0. Answer should be A. No matter you want you using the upper path, that path to do calculation to find your potential difference across X, Y, or you want to using the bottom part. Finally, at the end, you will get the same answer. Okay, is that clear? No matter you using which side to solve your problems, you will get the same answer. Okay, Fawa, okay, how about others? Manjo, okay. Okay, if okay, then it goes to your page number 5. This is all single loop. You see, the question that I found is single loop. Okay, so you need to be careful with your total current, with your direction of total current. Okay, here we found out that you see they will provided your overall current direction. So from here, I know that I know that this one 3 volt and 2 volt is same direction as the direction of current label in the diagram. So I know 3 plus 2 minus the opposite one. So after that at here, this one doesn't provide it, but we use the higher EMF minus the smaller EMF. Okay, so basically it's like this. Okay, we goes to the second page number 5. If let's say now we are not single loop anymore, how we solve with the multiple loop? Okay, here you need to label every branch for their current, current. So please, every single branch we label the current current. What is the current at here and here? At what is the current at here and here? We label. Okay. Then after that, you need to find out Kirchhoff's first law for every single loop. Kirchhoff's first law is current. Okay. Then find out the Kirchhoff's second law. Kirchhoff's second law for all independent loop inside the circuit. For unknown the current, sometimes we need to using mathematics simultaneous equation to solve lah. Okay, we go here. So this one is a battery of EMF E and negligible internal resistance is connected to four resistors of resistance R1, R2, R3. The current is I1 and I2 in the resistor as shown. Which equation is correct? Okay, dear. Do it and then tell me A, B, C, D. Which one is correct? Wow. Wow, no. Check. Wesley also no. Manju also no. Hmm? Fatima also no. Oh, all of your answer is correct. All of your answer are the same, but this is not the answer. Washini, Washini. All your answer are the same just now, but it's not the correct answer. Jore correct. Jore correct. Okay, so you look at my working step, ah. Do you guys agree? From this multiple loop, I got two equations here. Washini also no. Only Jore correct. Fawa correct. Fawa correct. Okay, dear here. So from these two, then you see for the answer at here, they combine I1, I2, and then got I3, I4. So that means that I have to think how to link these two formula together. Because in the A, B, C, D, we got I1 and I2. We got the R1, R2, R3, R4. So we have to think how to link. Okay, how to link? So at here, we can using here either plus or minus. If here we minus, if let's say we're using minus 1 minus 2. So E minus E will be 0. Then E1 R1 plus R2 minus I2 R3 plus R4. So your answer should be B. If you add it up together, then it should be 2E equals to I1 R1 plus R2 plus I2 R3 plus R4. So here this answer is wrong. If A, it should be 2E, not 0. If E, how do E? E is either I1 R times R1 plus R2, or E equals to I3, I2, then times R3 plus R4. So C and D is wrong. So is it okay? But just now all the answer kept giving me C, answer C. Plus it together. If you plus it together, it should be 2E, dear. If plus it together, this part should be 2E. Okay, is that clear, this one? Okay. So dear, if okay, we go to question number 2. The circuit shows contains a resistor S. Oh, okay, here, this is a resistor S. Okay, then Kirchhoff's law can be used with the data in the diagram to deduce the resistance of each of the two identical resistor label R. They want you to find what is this value for R. That means that here we got few paths. You can choose like this. But this path I cannot find R because I didn't involve with R at all. So cannot. Okay, we don't choose this path. So we can choose like this. Can we choose this? Also cannot. Why? I don't know S. I want to find R, but I have another unknown S. So this is not a good idea. Okay, then we choose again. Going here, going down. Can I choose like this? Yes, I got 2R, but this 2R is identical. This 2R is identical. So later on, I can find out just divided by 2 lah. Okay? Then I didn't include the unknown S. So it's more easier. Others physical quantity is known. Okay, so we will choose this path. Okay, so can you try and then tell me what is your resistance value for each resistor R? 1R only. The hints are, don't forget just now that I told you, label all the current in the branch. Label all the current in the branch. So at here, 4 going in, out is 3. That means here another 1 out is 1 ampere. So here is 3.0 ampere. Then this one is going out 0.5. So that means that here is 2.5 ampere. First step, label all the current. First step, label I in all. Okay. First step, label all the current in every single junction. Label all the current. Apply Kirchhoff's first law. Then after that, apply Kirchhoff's second law. Fatima. No. Check again. Any point the current that you apply, is it correct or not? Then first you check, Fatima, you check whether the current at every single branch, is it the same as me? Or the current that you label in the branch, is it same as me? Because current is so important. Later on, when we applying Kirchhoff's second law, is the EMF equals to the voltage across the component. You must using a correct current. Vashini, correct. Wesley, correct. Yes. Okay, so we're using Kirchhoff first law. Okay, second part, Kirchhoff second law. Okay, the EMF equals to the potential difference. Okay, EMF equals to the potential difference. So total EMF is 12. Potential difference. So it's 1.0 ampere times the R plus 1.5 times R. Yeah, that's all. Oh, one more. This one, internal resistance. Plus Internal resistance is 4 times 0.5. So at the end, I should get 4.0 ohm. Okay, here. This part voltage, this part voltage, and this part voltage. V1, V2, and V3. Okay, those you cannot solve, then you look at my working step here. First step, all the current in the branch we label. Must label and do it correctly, because the current we will use it apply to calculate the potential difference for the Kirchhoff second law. Okay, then after that you need to choose the path that you want to use because this is series and parallel circuit, so you have to find the suitable loop. Okay, so I choose the blue color loop is because there is only one unknown, which is the R. Okay, so 12 volt is the EMF supply in the circuit. Then voltage drop due to the resistor or internal resistor is the 1.0 ampere flowing through the resistor R. Why is 1.0? Because 4 ampere go in, 3 ampere out. That means 1 more ampere is going out by 1.0 ampere. Then blue color going to a second R. What is the current flowing through the second R? Answer is 1.5 ampere. Why is 1.5 ampere? 1.0. Before is 1.0. After resistor R is still 1.0. This part is still 1.0. Then the current flowing through the component S is 0.5. 1.0 is in. 0.5 is also in. So 2 in, 1 out. Out is 1.5. 1.5 times R. And then just now I also careless. I thought until here is already finished. I never here, be careful here. There is one internal resistance. We also need to consider. The internal resistance is current, overall current flowing through it. Okay? So it's which is 4.0. Because 2.5 plus 1.5 is 4.0. Or here, starting with 4.0, no matter how they split, at the end go out. Here also 4.0. So my answer will get 4.0 is answer A. Sorry, answer B. Okay, until here, is that clear? Now we joining Kirchhoff first law and second law. Every single junction, please find out their current carefully. Okay? Then choose the path that you want. Choose the loop that you want. Apply Kirchhoff second law. Okay, until here, is that clear? Any question you want to ask me? Can we proceed to the question number 3? Questioning okay? Mama okay? Manjo, is it okay, Manjo? Okay, Manjo okay. Okay, dear, here. Okay, can you find out what is your I1, I2, I3? So actually at here, first, I give you some hints. We need to using simultaneous. Okay, the most easiest one is Kirchhoff first law. Every single branch we using we label the current. So from here, this is positive current is going here. This is I1. Why I1? Because here, labeling I1. So this part also I1. Okay, so here, this one positive is here. So current is flowing up from positive terminal. This is I3. Why I3? Because here is I3. So first equation, I can know that I1 is going in. Then I3 is going in. I2 is going up. So this one is first equation. Okay, using Kirchhoff first law, answer first equation, I1 plus I3 equals to I2. Jore, correct. Okay, Wesley, no. Then you goes for the second loop. You choose others loop. For me, I can choose this path, this loop. Okay, I label this one is loop, maybe loop 1. Okay, loop 1. So at here is 15 volt. Actually, 15 volt will be equals to the I2 times 2. plus I1 times 2. So at here, 15 equals to 2I2 plus 2I1. So I got second equation. Then we goes to loop, another loop 2. 9 volt equals to I2, 2I2. Okay, 2I2 plus 2I3. This is third equation. Okay, the rest is you using a mathematics simultaneous to solve the question. Mathematics simultaneous to solve. Washini correct. Those who cannot, you can refer to my working step. Okay, I'm done. Power correct. Manjo correct. Yeah, the rest actually is just mathematics. The concept at here is you need to find a different rope. Okay, apply Kirchhoff's second law. Then the most easiest one is Kirchhoff's first law, the current in the branch. Then you find this, find this. Actually, you tell me, teacher, I want challenge myself. I want to using the largest loop, can or not can. You will also get the same answer, but you need to be careful. You see, the polarity of the terminal of battery is different. Okay, so until here, if no problem, then we go to the page number 7. Is it okay? For those still cannot identify what is the mistake or maybe do substitution wrongly, you can print screen or later after that I have the video recording. You can refer again. Okay, if no question, we go to page 7. Is it okay? Okay, let's go. 2018, 4 different resistors are arranged. A current 1.5 go in, okay? Then out from the junction Y, what is the current in the resistor of resistance 30 ohm? So that means that here, what is the current at here? Okay, try. Those have no ideas? Refer to me. I redraw the circuit and show you. Okay, what is the idea? Any of you got the answer? What is the ice free? Manjo Manjo? Yes, Manjo correct. Correct, yes, Manjo correct. Washini correct. Yeah, Manjo, yeah. How about others? I already draw out the diagram, trying to simplify the diagram. Okay, so at here, Kirchhoff's first law. So we know 1.5 is equals to the I2 plus I3. Now we want to find I3. Okay, then how? So we know that voltage for 70 ohm equals to the voltage for 140 ohm. Am I right? Parallel ma. Okay, so this one is I2 times 70 equals to I3 times 140. So at here, I2 is actually 2I3. Okay, so this one here, I2 is actually 2I3. I3, you look at here, 70 ohm and 140 ohm. 70 ohm is less resistor. Of course, it will be having higher current. Since it's half of the resistance of 140 ohm, that means that the current will be double up. If I explain in word, actually from the relationship we surely know this one is double A, double current. But I still showing you how to get double current of I3. Okay, so at here, because resistance become half of it, so current will be double up. Okay, then at here, 1.5 will be equals to 1.5 will be equals to I2 plus I3. I2 is double I3 plus I3, 1.5. So 1.5 equals to 3I3. I3 is 0.5 ampere. See, answer here, 0.50. So paper 2, 50 ampere. Okay, I explain one more time. I explain one more time. Okay, this one, if we rearrange, seems like complicated, but actually you can just redraw. These three blue color, they are in series. So I redraw. In series, I found out, A total is 140 ohm. Just now, the upper part is 70 ohm. The resistance is half of the 140 ohm. That means that the current will be double up. This one is I, this one will be 2I. Agree? Agree? 70 ohm, lower resistance, higher current. Then now it's exactly half of 140 ohm. So my current should be double up, 2I. So in total, go out is 3I. Then 1.5 ampere going in will be shared by 3I. Each I is actually 0.5 ampere. Teacher, why the current in 140 ohm is the current for 30 ohm? Because 50, 30, and 60 ohm, these three resistors, they are connected in series. Their current should be the same. And you have to consider their total current, then only can find their total current, total resistance, then only can find their total current flowing through them. So the current flowing through this 140 ohm actually is the current flowing through 50 ohm, 30 ohm, and 60 ohm. They are the same. So boys and girls, did you able to get my answer? 0.50 ampere. Is that clear? Okay, Any others? Because if you clear, then that's all for our lesson already.